Today, we're jumping into one of the most intuitive and frankly common sense algorithms in all of machine learning, k-nearest neighbors, or KNN. And here's the thing, you might not know the name, but you already use the core idea behind it every single day. Okay, so let's just start with a really basic question. Imagine you're at a farmer's market and you see a piece of fruit you have never ever seen before. How do you even begin to guess what it is? Well, you'd probably look at the fruits sitting right next to it, right? Are they with the apples, the berries? That basic problem is exactly what KNN was built to solve. And yeah, the answer is really that simple. You figure something out by looking at the company it keeps. If that mystery fruit is sitting in a bin full of oranges and it's round and orangish, you're gonna guess it's probably some kind of citrus. That simple intuition, that's the engine behind a surprisingly powerful algorithm. So let's put a slightly more formal frame on this. The whole idea behind k-nearest neighbors is that similar things tend to exist close to one another. Birds of a feather flock together, right? It's a basic pattern of the universe, and K9 just takes brilliant advantage of it. Okay, so here's the textbook definition. KNN is what we call a supervised non-parametric algorithm. Now, supervised just means we give it a bunch of data that's already been correctly labeled, kind of like that produce section where we already know which bins hold apples and which hold oranges. And non-parametric means it's flexible. It doesn't try to force our data into some neat, predefined box or equation. So, how does this actually work when you're using it? Well, it all boils down to making just two key decisions. It's actually pretty straightforward, so let's break them down. First, you have to choose K. And K is just a stand-in for the number of neighbors you're going to listen to. Are you going to ask just one neighbor for their opinion, or maybe 5 or 10? And second, you have to decide what close actually means. How are you going to measure that distance? So let's take the simplest possible case. If we set k equal to 1, then a new data point is just given the label of its single closest neighbor. That's it. It's a one-on-one poll. Super fast, super simple. But you can imagine it can get thrown off pretty easily by a single weird piece of data. Now, what happens if we set k to something like 5? This is where things get a lot more reliable. We find the 5 closest neighbors, and we basically take a vote. If 3 of them are class A and 2 are class B, guess what? Our new point becomes class A. And here's a little pro tip. You'll often see data scientists pick an odd number for k. Why? Well, it's a simple way to avoid annoying ties in the vote. This brings us to that second big choice. We keep saying closest neighbors, but how do we actually calculate that distance mathematically? This is where we need to pick what's called a distance metric. And this slide lays out the 2 most common ways to do it beautifully. On one hand, you've got Euclidean distance. This is what you learned in geometry class. It's the direct, straight-line path between 2 points. You know, as the crow flies. On the other hand, you have Manhattan distance. Think of it like you're in a city grid. You can't just fly through buildings, you have to go block by block. Which one you choose really just depends on what your data actually represents. All right, so the theory makes sense, but where is this simple little algorithm actually being used? You might be surprised at just how common it is. I mean, it is pretty much everywhere, from the movies that streaming services recommend to you, to really important stuff in finance and healthcare. KNN is all over the place. It's a workhorse for pattern recognition, and it's even used to help clean up messy data before you do anything else with it. Its simplicity makes it this awesome, versatile tool for a ton of different problems. Let's make this super concrete. Say you apply for a loan. A bank can use KNN to take your profile, your income, your age, your debt, and compare it to thousands of past customers in their database. If your nearest neighbors in that data were all people who paid back their loans on time, the algorithm's going to predict you're a pretty good bet too. And here's another great one, the post office. Ever wonder how a machine can read that handwritten zip code on an envelope? A lot of the time, it's KNN at work. It takes an image of that squiggly 5 you wrote and compares it to a huge library of other handwritten 5s to find the closest matches and say, yep, that's a 5. Now, no algorithm is perfect, right? And KNN is no exception. It has some really clear strengths, but also some major weaknesses. And it's super important to understand both sides of the coin. So, if you want to understand KNN's pros and cons, you have to understand this one key idea. It's a lazy learner. And that's not an insult, I promise. All it means is that it doesn't do a big, complicated training process up front. Instead, it just memorizes or stores the entire data set. All the heavy lifting, all the math, happens at the very last second, right when you ask it for a new prediction. And that has some big consequences.
And that lazy approach leads to this really clear trade-off. On the plus side, it's super easy to understand and implement, and because it's just using raw data, it adapts to new information instantly. But on the downside, because it has to compare a new point to every single other point in the dataset, it can get incredibly slow with large amounts of data. It just doesn't scale well. It's also prone to what we call overfitting, and maybe most famously, it suffers from the curse of dimensionality.
So what on earth is this curse? Well, imagine you're comparing people based on just two things, two dimensions, height and weight. It's pretty easy to find who's close to you. Now imagine we add 100 more dimensions: income, zip code, shoe size, favorite movie. In that massive, high-dimensional space, everything starts to get really, really spread out. It gets to a point where every data point is about the same huge distance away from every other point. The whole idea of a local neighborhood starts to lose its meaning, and the algorithm breaks down. Okay, so with these limitations, it can be slow, it struggles with lots of features. You might be wondering, why are we still talking about an algorithm whose core idea is over 70 years old? Well, because its role in data science is absolutely fundamental. I mean, the initial concept was floated all the way back in 1951, and yet here we are today, and it's still one of the very first things anyone learns when they start studying data science. Why? Because it's the perfect way to build your intuition. It teaches you the core concepts of classification and how to think about distance in data like nothing else can. And that really brings us to the ultimate takeaway here. The thing that makes KNN so fantastic, its elegance, its beautiful simplicity, is also the source of all its biggest problems. It's a perfect reminder that in machine learning, there's no free lunch. There is always a trade-off.
So I'll just leave you with this question to think about. In a world where we're always building bigger, more complex models, when might the best, most powerful answer be to just stop and simply look at what's right next to you? Thanks for tuning in.